Theory of relativity. A complete theoretical framework. Historical context and motivation. The theory of relativity arose from discrepancies in classical physics and challenges in reconciling Newtonian mechanics with electromagnetism. The pivotal issues included: Newtonian mechanics assumed 1. Space and time were absolute and independent. 2. Gravity acted instantaneously over a distance. Maxwell's equations, 1865. 1. Unified electricity and magnetism, predicting light as an electromagnetic wave traveling at a fixed speed, c. 2. This raised the question of the luminiferous ether as a medium for light propagation, which contradicted the principle of relativity. Michelson-Morley experiment, 1887. 1. Failed to detect Earth's motion through the ether, undermining the ether hypothesis and Newtonian absolutes. Einstein resolved these contradictions with two groundbreaking theories. 1. Special relativity, 1905, deals with non-accelerating frames and establishes the relationship between space and time. 2. General relativity, 1915, extends relativity to include gravity and acceleration, redefining gravity as spacetime curvature. 2. Special theory of relativity, STR, 2.1. Foundational principles. Principle of relativity. 1. The laws of physics are the same in all inertial frames of reference, frames moving at constant velocity relative to one another. 2. There is no preferred inertial frame. Invariance of the speed of light. 1. The speed of light in a vacuum, c, is constant for all observers, regardless of their relative motion. 2.2. Core concepts. 2.2.1. Relativity of simultaneity. 1. Events simultaneous in one inertial frame may not be simultaneous in another. 2. For example, two lightning strikes at different ends of a train appear simultaneous to an observer on the train platform, but not to a passenger inside the train. 2.2.2. Time dilation. 1. A moving clock appears to run slower compared to a stationary clock. Where 2. Formula. Delta T equals delta T, frac 1 minus V2, C2, delta T. Proper time, time interval in the clock's rest frame. Delta T, observed time interval. V. Relative velocity of the clock. C. Speed of light. 2.2.3. Length contraction. 1. Objects in motion appear shorter along the direction of motion. 2. Formula. L equals L0, sqrt 1 minus V2, C2. 3. Where L0, proper length, length in the object's rest frame. L, observed length. 2.2.4. Mass-energy equivalence. 1. Mass and energy are interconvertible. 2. Famous formula. E equals mc2. 3. Where E, energy. M, mass. C, speed of light. 2.3. Lorentz transformations. These equations relate the space and time coordinates of an event in two inertial frames moving relative to each other at a constant velocity, v, spatial transformation. 1. X equals gamma, x minus vt, temporal transformation. 1. T equals gamma, t minus vx, c2, where 1. Gamma equals 1, sqrt 1 minus v2, c2, Lorentz factor. 2. X, t, space and time in the stationary frame. 3. X, t, space and time in the moving frame. 2.4. Implications of STR. 1. Unified space and time into spacetime, where time is the fourth dimension. 2. Overturned the Newtonian concept of absolute space and time. 3. General theory of relativity, GTR, 3.1. Fundamental idea. 1. Gravity is not a force but a curvature of spacetime caused by mass and energy. 2. Massive objects distort spacetime, and this curvature determines the motion of objects in light. 3.2. Core principles. Equivalence principle. 1. Acceleration and gravitational effects are indistinguishable in a local frame. 2. A person in a closed accelerating room cannot distinguish whether the force they feel is due to gravity or acceleration. Curvature of spacetime. 1. Described by the Einstein field equations, gmn plus lambda gmn equals 8 pi gtmn, c4. 2. Where gmn, Einstein tensor, spacetime curvature. Lambda, cosmological constant. Tmn, energy momentum tensor, matter and energy distribution. 3.3. Predictions of GTR gravitational time dilation. 1. Time runs slower in stronger gravitational fields. 2. Formula. Tf equals Tsqrt 1 minus 2 gm, Rc2. 3. Where. 4. G. Gravitational constant. 5. M. Mass. 6. R. Radial distance. Gravitational lensing. 1. Light bends around massive objects due to spacetime curvature. Perihelion precession of Mercury. 1. The orbit of Mercury shifts due to spacetime curvature near the Sun. Gravitational waves. 1. Ripples in spacetime caused by accelerating massive objects, first directly detected by LIGO in 2015. Black holes. 1. Regions of spacetime with infinite curvature, where even light cannot escape. 3.4. Mathematical framework. 1. Geodesics. Objects move along the straightest possible paths in curved spacetime, geodesics. IV. Implications and applications. 4.1. Scientific impact. 1. Unified mechanics and electromagnetism under a relativistic framework. 2. Laid the foundation for modern astrophysics and cosmology. 4.2. Technological applications. 1. GPS. Accounts for both gravitational and velocity-related time dilation. 2. Particle accelerators. Incorporate relativistic mass and energy transformations. 4.3. Philosophical implications. 1. Time and space are relative and intertwined, replacing Newtonian absolutes. 2. Redefine causality and simultaneity, challenging classical notions of the universe.